Okay. Hi, everyone. Hi. So, first off, let me tell you that your grades for midterm exam are released. Please take a look at them. And also, please participate in the class. I appreciate it if you do so. And the goal of this course is only learning and enjoying learning, right? And that's another thing I wanted to say. Yeah, okay, let's so last session we talked about RNN and oh, by the way, I forgot to say that also assignment 2, don't forget to do that, right? It has 20% of your total grades. When is its deadline? In a week, right? No,
Sunday.
November 19th, you said?
Sunday.
Okay. Sunday midnight. Okay. So don't forget that, please. Okay, so last session we talked about RNN and LSTM, and then we started attention. Let's restart from attention slide deck very fast. So, as I said, when we look at, for example, an image such as Mona Lisa portrait, we only attend to some parts of the image, right? Or some pixels of the image. Or when we are doing fast reading, such as skimming, we only consider some of the important words and we ignore some less important words, right? In other words, we attend to some pixels or words, to some elements. In mathematical way, we are weighting data, right? So, and we said, consider an autoencoder where we have encoder, decoder, and in the middle of the autoencoder, we have a hidden space or latent space, where the concept of that thing will be in the hidden space. And we said that this autoencoder can be used, for example, for domain transformation, such as transforming a cartoon elephant to some real world elephant, right? And then we said that embedding vector in the latent space, let's call it context vector, assume it is p-dimensional. And then I said, so we have encoder layers, decoder layers, as you see in this figure, and we have one context vector, which is equivalent to the last hidden vector of the encoder, right? This is sequence-to-sequence model without attention. And then we said, so this is, we said, for example, RNN and LSTM are like that when they are implemented as an autoencoder. And then we said, what if we have sequence-to-sequence model with attention? And then I said, in this case, the difference is that we have several context vectors, where each context vector is a linear combination of all of the hidden vectors in the encoder, right? And this linear combination has some weights, and this weight is attention. A is standing for attention, right? And also I said we can calculate similarity between the output, every output word in the output sequence, and every input word in the input sequence. And I said an example where our input, for example, is a sentence in English, and output is a sentence in Persian, which is translated. And I said the corresponding words in the two languages attend to each other more. So we can find out the similarity or attention between the output words and the input words, right? And then I said this similarity scores that we calculated, they are not between the 0 and 1, so they are not like probability. Let's make them behave like probability and Gaussian probability. Then I said for that, we can use softmax form, where softmax form, in this case, they will add to 1, and they will be between 0 and 1, and they will be like Gaussian distribution. So when we put them in the softmax form, they become attention score, which is like probability, Gaussian probability. We talked about this is also an example where every word attends to some other of its previous words, assuming that this is a causal model, only attends to its previous words, right? Also, I said that context-aware embedding is important. I said some examples where vegetation is in the bank of river, and also money is in the bank. These two banks are different, but if we use non-context aware embedding methods such as word2vec and glove, they would have the same embeddings for the both bank words in these two sentences. But context aware embeddings such as I think Elmo, BERT, GPT, these things which for example BERT and GPT, where they use attention, they are context aware, and in those cases we will have different embeddings for these two bank words in the context, depending on the context. Also, did I mention the context principle by Frege in philosophy? No, I think I will do that. Hopefully I will do that in this session. Okay, so consider a database. Have you passed any course on database? No. So database is just, it has some keys and values, right? And we have some query. When the query comes, we compare the query to the keys. So we have each row has one key and one corresponding value. And the query comes, and then it is compared to the keys, and assume it is equal to the key 2. Then the output will be value 2, the corresponding value to that key which matched to the query, right? This is how it is done. But as you see, comparing with the whole rows, especially when n is large, is very time consuming. That's why they have proposed some algorithm called hash table or hash coding, where they do this search fast. But it's out of the scope of this course. We don't care right now about that. I'm saying that they use hash tables for searching very fast, for matching, for finding matching keys to the query. And for example, in Python, hash tables are implemented in dictionary. Whenever you are using dictionary, you are using hash table. Okay, so as I said, in regular database, query matches with one of the keys, one of the rows, and the value of that row comes out, right? But now let's use soft query retrieval. So that was hard query retrieval. Now what is soft query retrieval? Soft query retrieval says that let's calculate the similarity of the query with each of the keys in the rows, right? And see, for example, it is very similar to key 1, a bit similar to key 2, less similar to key 3, very similar to key n, etc., right? And then we find some weights of similarity, and then we let the value, output value, be the linear combination of all of the values with the same weights that we found between the query and key. Okay, so that's exactly what it is. The attention, as you see, is a linear combination of all of the values with the attention values, right? You see that? AI. AI is the weights that I just said. And how do we calculate AI? So first we calculate SI, which is similarity between the query and the keys. So Q here stands for query. KI stands for the ith key. And then it gives us some similarity score, but for this to be Gaussian distribution, we use it in softmax form, right? Softmax form. Then it gives us AI, which is the weight. And these AIs sum to 1, and they are between 0 and 1, and they have Gaussian distribution. And then we use these weights for linear combination of all of the values. This is the output value that we'll have, right? Okay, this is soft query retrieval, as you see. Okay, so Q for query, KIs for keys, and VIs for values, right? So as you see, attention can be seen as a soft query retrieval also. So these are the formulas. If we want to visualize them, it's like this. So we have, for example, in this case, we have 4 keys. We have 1 query. We calculate S1 to S4 for the similarity of the key to each of the query to each of the keys. Then we find the AIs, right? Which was using softmax. That's why it's dense, because softmax uses all of them. In its denominator, it uses all of them, right? And then after this, this is a linear combination of all of the values with their with the calculated weights, right? And this gives us the attention, right? Okay. The similarity SI can be any notion of similarity, right? Can be any notion. So the most simple one is the inner product. For similarity of two vectors, it's inner product, right? So for SI, we can say Q transpose KI, the inner product between the query and the ith key, right? We can also scale it, scaled inner product, where we say Q transpose XI, but scale divided by the square root of P. And what is P? Recall that. Yeah, P I think is the dimensionality if I remember. Give me a sec. Yes, P is the dimensionality of query and key, because they have the same dimensionality. Otherwise, we can't do inner product, right? So P is the dimensionality of query and the key. These are vectors, right? And also general inner product, we can say that Q transpose KI, but in the middle we have W, matrix W, right? Some matrix hyperparameter. And W is also P by P. By the way, WQ and WK, which are used in the fourth one, additive similarity, they are learnable parameters, learnable matrices and vectors, right? And they are learned by backpropagation. So additive similarity says that W transpose Q plus WK transpose KI. In other words, if query and key are in the same direction, they will be added. But if they are in different directions, their addition becomes very small. So you can see this addition is also kind of a similarity measurement, right? Am I right? So among these, the scaled inner product, which is this, is used most often in attention. Okay. So this attention that we talked about calculates the attention of a target word or query with respect to every other input word or keys, right? So we have some query word, and all other words in the sentence, all of the words are the keys, right? So basically, we can calculate how similar every word is to every other word, right? By the way, when I say word, I mean the token in the sequence. It can be pixel also. So using equations, so x6, we see how similar the other words of the sequence are to that word, right? In other words, how impactful the other words are on this word, right? Example, I am a student. Let's consider we are processing the word student, okay? So the query becomes a student, and the values are I, am, and a, the other words, right? So because we have 4 words here. Then the normalized similarity assume the weights, I mean the normalized after softmax. The weights become 0.7, 0.2, and 0.1. So 0.7 for I, 0.2 for M, and 0.1 for A. Basically, it says that 0.7 is the similarity of a student and I, 0.2 is the similarity of student and M, and 0.1 is the similarity of a student and A. And as you see, there is sum to 1, right? The attention then becomes 0.7 value of I plus 0.2 dot value of the word M plus 0.1 dot times value of the word A, right? Okay. Let the words of a sequence of words be in a d-dimensional space. What do I mean? Assume my words can be, I can see every word in my sentence as a d-dimensional vector. How can I do that? Simply, I can use word-to-vec embeddings of the words. For example, in word-to-vec, I think d-dimensionality is 100 and something. I don't remember, 120, 150, right? So every word can become a vector. And this, as I said, can be taken from any NLP method such as word-to-vec or GLOVE, right? Then the query, key, and value are projection of the words into p-dimensional and r-dimensional subspaces. So here in attention, we are not considering xi directly as qi. After some linear projection, we calculate qi with some weights, right? What is this? Recall preliminaries. It's projection of xi onto the column space of matrix WQ, right? And this matrix, you can see this as one dense layer of neural network. Do you remember? We talked about it. Every fully connected layer can be seen as a linear projection before activation function, right? So you can see each of these as one layer of neural network, fully connected neural network. WQ, as you see, these are different Ws, different weights. So using different weights, using linear projection onto the different weights, I can find query, key, and value, right? And WQ, assume it's D by P, so it projects onto the p-dimensional space, so it becomes p-dimensional query. WK is D by P, it projects onto another p-dimensional space, therefore K becomes p-dimensional. WV is D by R, so it projects onto an r-dimensional subspace, so value is r-dimensional. Can you tell me why query and key should be the same number should have the same number of dimensions, but value has different number of dimensions? Why these two should be equal to each other in terms of number of dimensionality? Because as you saw, we need to calculate the inner product of query and key, so they must have the same dimensionality, right? But value can be different dimension, can have different dimension. Okay. Now, assume I put the queries next to each other column-wise to make matrix Q, put the keys next, so n keys, I have n words in this sequence, n keys next to each other to column-wise to form matrix K, and the nv's stack them together column-wise to make matrix V. Also, you can put the embedding vectors of the words next to each other column-wise to make the matrix X, right? Notice the dimensionalities, right? Now, can you tell me that, so what was Q transpose Ki in this sense? Q, according to this and this. So replace equation 13 and 14 in the inner product that we had. It becomes Xi transpose WQ, because Qi is WQ transpose Xi. So Q transpose becomes Xi transpose WQ. And Ki, according to this, is WK transpose Xi. As you see here in the middle, I have WQ, WK transpose. Ignoring this middle part, I have Xi transpose Xi, which is inner product, right? And you can see Xi transpose Xi as also kernel. Kernel is an inner product, right? But in the Hilbert space, right? So, but we know that kernel is symmetric, is a symmetric function. If both of these were similar weights, WQ, WQ transpose, then this would be exactly some kernel. But it's kind of a kernel, not a kernel, because it's not symmetric. Okay, that's another thing we should notice. Attention measures similarity. Kernel also measures similarity. So there is some connection between kernels and attentions. So do you remember what we had in the previous slides? I'm talking about these. So I'm talking about these. Exactly. So what was this? For example, Q transpose Ki over square root of P. Remember? One of them. So we had several ways to calculate the similarity. One of the most important, famous one is this. Now, can I write all of these things in matrix form? Yes. So try to have a mental picture of this slide. So AI is so first I have Si, which is inner product of Q and K scaled by 1 over square root of P, and then I put them in the softmax then I use these softmax weights in the linear combination for the values, right? So let's see and go to this slide, and I want to write this in matrix form. It's here. So do you remember we had Q transpose Ki, but now in matrix form it becomes Q transpose K for the n words, all of them, right? So what is this? It's basically calculating the similarity of all of the Qs, queries, and all of the keys pairwise, right? And I divide it by square root of P, right? And then I put it inside the softmax. It gives me the AIs, right? And then I have linear combination of the values. But value comes here at the left-hand side because of the dimensionality matching in the matrix multiplications, right? So this is attention, and this attention is R by N because of the dimensionalities. If you consider these dimensionalities that I just talked about, it becomes R by N. By the way, this softmax is applied element-wise. What do I mean? So let me see. Q is P by N. So Q transpose is N by P. K is P by N. So the whole thing is N by N inside the softmax. V is, let me remember. V is R by N. I guess, yes, softmax applies on every row of its input. What do I mean? So its input is N by N. N by N. And every row, we apply softmax on it, right? So as a result, after the softmax, every row sums to 1. Okay? So softmax is applied on elements of every row. And then in this case, after softmax, we still have N by N matrix, but every row will sum to 1. Did you get my point? Okay. So this is attention. And by the way, if queries, keys, and values are all from the same words in the sequence, it is self-attention because it is calculating attention to itself, right? Self-attention. In a few slides, we'll see another kind of attention, which is cross-attention, okay? So attention can be used, is not just for natural language processing. It can be used for computer vision as well. Remember, I said, assume you look at Mona Lisa, so you can attend to different pixels. So for example, we can consider the extracted low layer features, which are different parts of the image. Consider different parts of the image, okay? And then we can get, just give me a second. So for example, we'll have this, consider a patch which goes over the different parts of the image, right? Then can I calculate the attention of every patch to every other patch? Right? I can do that, right? This is possible to do that. So I can have attention between the different parts of the image. Also, you can, for example, consider this figure A. What is it doing? It's caption generation for images. So basically, it gets image as input. It outputs descriptive caption for the image, right? For example, if we give some input as an image as an input, and it outputs elephant is, for example, is swimming in the water or something like that. So as you see here, you can see it as an autoencoder, where encoder part is convolutional neural network because we have image as input, and then it gives me some feature vectors, and then I feed it to some LSTM in the decoder, and the LSTM I train it so it outputs some words, right? And then so we can have self-attention on the image. We can, so in figure B, I'm saying that I can consider the attention of every patch of the image to every other patch of the image. Then in this case, for example, this patch on the head of the elephant attends more to the patches of the body of the elephant than to the corner of the image, right? So we have different attention scores between the different patches of the image. By the way, also for this specific application, for example, the model learns to attend to some important parts of the image rather than to non-important parts for describing the caption. For example, for generating the caption, of course, the patches around the containing the elephant are more important than the patch here in the bottom left corner. Right? For example, this patch is also important because it explains the water. So that's one thing. As I said, attention can be used in different fields of science, not just natural language processing. Many papers which are using attention for different fields of science, they have this kind of title: attend, tell, and do something. Okay, they usually have this in title. For example, attention so some examples are attention caption generation for images. Its title is show, attend, and tell. You can see these references to see these titles in them. Caption generation for images, show, attend, and tell. Caption generation for images with ownership protection, patent, and these things, or watermark. Protect, show, attend, and tell. Text reading from images containing a text. Show, attend, and read. Translation of one image to another related image, such as cartoon image to real image, something like it. Show, attend, and translate. Visual question answering. Show, ask, attend, and answer. Human-robot social interaction. Show, attend, and interact. Speech recognition. Listen, attend, and spell. All of them are using attention in them. So as you see, attention has been used in image processing, in natural language processing, in the speech processing, in all of them, right? Because you can see all of them as sequences. Of course, text is a sequence of words. Speech is a sequence of phonemes, right? But how is image a sequence? You can see image as a sequence of pixels or patches, right? So you can see image also as a sequence of patches. And we know that in a sequence, order is important. Of course, in an image, order of pixels is important. If you shuffle the pixels of an image, the image will be ruined, right? Okay, so far we talked about attention. Now let's talk about transformer, which makes use of attention. So do you remember autoencoder that we talked about? Right? It takes input data, embeds data into a context vector, which simulates a concept in human's mind. For example, you get, when I say cartoon elephant as input, output is an real elephant. In the middle, I have the concept of elephant, exactly the same as the concept of elephant as that is in your mind. Whenever I talk about elephant, you will remind some concept of elephant in your mind. But is that elephant in your mind a gray elephant or a white elephant? A fat elephant or a thin elephant? No, it's just elephant, the concept of elephant, right? So exactly it's like that, and generates an output, right? By the way, this concept is also related to epistemology in philosophy. So the concept, so in epistemology, we have universals and we have particulars in epistemology. Okay. Hegel and Kant have talked about these a lot. So universals, oh, by the way, Plato has also talked about this a lot in his theory of forms. So particulars are the things that you can see, for example, table, human, etc. Right? Everything that we can see in this world is particular, and some philosophers say that we have some true images of these in a world of logic. For example, Plato has said that. For example, whenever we see a table, we see a lot of tables, but we have a true table in the world of logic. And that true table doesn't have any shape. Because why? Because we might have rectangular table, we might have round table, anything, right? We might have, also it doesn't have any particular color because we might have brown table or red table, all of these. So the concept of the table is that in that world, and these are called particulars, right? Universals is exactly what can be shared between particulars, such as color, such as shape, such as unity, one table or several tables. Right? These are called universals, and I think universals here are what we are talking about. So which is shared between things, but the concepts you can see them maybe as the true forms of particular. So I said that's also related to that. Where were we? Okay. In other words, the autoencoder transforms the input to some related output, as we saw. Okay. An example of this transformation is translation of one sentence to another, from one language to another language, right? Another example is image captioning. Input is image, output is text describing the image. So an autoencoder can be named transformer. Why? Because it transforms one domain to another domain, right? So the name of transformer comes because of this, because it transforms something to something, right? And yeah, it's for transformation. So the structure of transformer is illustrated here, as you see. A transformer is an autoencoder which has encoder and decoder. Okay, but let's go into the depth of these things and see, explain in detail what the encoder and decoder of transformer are. So first, encoder of transformer. So the encoder part of transformer embeds the input sequence of n words into context vectors with the attention mechanism. So do you remember, encoder gets the input and makes a context vector. This is exactly what it is doing, and it uses attention mechanism also in it, right? So we will explain later that transformer does not have any recurrence, and RNN or LSTM, such as in RNN LSTM module, right? So basically, before transformers, for sequence processing, we had to use recurrence, such as in recurrent neural network and LSTM. Both of them had recurrence. Even ELMO, which used bidirectional LSTM, do you remember last session? That also has recurrence. But transformer says that attention is all you need. This is the title of their paper. Attention is all you need. You don't need recurrence anymore, right? For processing sequence. As there is no recurrence and no convolution, the model has no sense of order in the sequence, right? So one issue happens. One issue that, how do we encapsulate the information of order? Because we know that in sequence processing, order is very important, right? In contrast to regular data where order should not be important. So as the order of words is important for meaning of sentence, of course, for example, I am well is different from am I well, right? These are very completely different sentences. So we need a way to account for the order of tokens or words in the sequence, right? By the way, token is the same as word plus some other things. For example, question mark and end of the sentence, start of the sentence, plus the regular words, they call these tokens in natural language process, okay? For this, we can add a vector. Now, what trick do they use? They say, okay, let's find some vector which encapsulates the information of position of every word in the sentence, and then add this position vector to the actual embedding vectors of the words, right? If we do that, after this addition, the embedding of the vectors will have the information of position in them. Do you get it? Now I will explain how they do that. So that's called the position encoding part. Now I'm talking about this. By the way, I'm going from down to bottom to up, explaining everything to you. So now here, we are here. What is it doing? So as I said, we have positional encoding some position vectors, we add them to the input embeddings. Here you see addition, right? But how do they do that? So consider the embedding of the ith word in the sequence, right? So I denote it by xi, and xi can be the word-to-vec embedding of the ith word. It doesn't have order in it, right? For encoding the position of the ith word in the sequence, we define position vector pi, which is also d-dimensional, right? Where the odd elements of pi are this, and the even elements are this, right? Where j starts from 0 to d over 2. What do I mean? So when j is 0, what happens? It becomes 0 element, right? So 0 element is this. Then set j1. So j0 gives 0 element, then 1. J equals 1. You tell me. 2, 3, 4, 5, etc. Do you see? Even elements, odd elements, right? And then you put these elements next to each other, it becomes the whole vector, right? Agree? But now let's analyze this. So what is I and what is J? Don't confuse this. J is for odd and even elements of the position vector, this vector, right? J goes from 0 to d over 2. Why d over 2? Because when j is d over 2, then you have covered the whole d dimensions, right? Because half of them are handled by this, half of them are handled by this, right? Agree? And what is I? Is the ith word in the sequence, right? I exactly is the position. The first, second, third, fourth, right? Now, why do they use sine and cosine? I'll tell you in this figure. Because of this. I'm visualizing those position vectors as a figure. So what are these? These are token positions. So these are i's. I equals 1, 2. What do I mean by I equals 1? It means the first word in the sequence, right? So this row is P1. This is the second row is P2, etc. Right? So I have depicted for 10 words, right? And now compare these rows. Do you see they are completely different? All of them are different. Do you see that? As they are different, it means that the information of position has been captured in these position vectors. And that sine and cosine makes this difference that you can see here. And another interesting thing is that the difference of position vectors concentrate more on the initial dimensions, because these are dimensions of position vectors, right? Agreed? As you see, most difference is here, usually initial dimensions of the position vectors, right? Okay, and that sine and cosine makes this difference. So far clear? So now I have the pi's. So now I add pi to every xi. After this addition, every embedding has the information of position in it. You see? Do you see that? For example, now consider the word I am glad I could help. I have two I vectors, right? But after this addition, the embeddings of these two will be different, because this is the first I, and the other one is the fourth I, right? Because P1 and P4 are different. Agreed? Although their word-to-vec embeddings are the same. Okay. So where are we now? We are here after this addition, right? By the way, what was this? This was word-to-vec that I told you. And what is this? This is PI, right? So we are here. Now, data are fed to multi-head attention module with self-attention. This, I'm talking about this part now. What is this? Do you remember the attention that we talked about? The self-attention. So it had query, key, and values, right? That's why I have three things here. Three inputs. These are the query, key, and value, right? And why is it self-attention? As you see, using the same thing, I'm using the same words in the sequence. I'm finding query, key, and values, right? So it's self-attention because I'm calculating attention of every word in the sequence to every other word in the same sequence, right? So that's another thing that is, so it's self-attention first off. And why is it called multi-head attention? Because I apply this attention for h times. What do I mean? These several repeats of attention is for this reason that I'm explaining. The first attention determines how much every word attends to every other word in the sequence, right? The second repetition is that the second repeat of attention calculates how much every pair of words attends to every other pairs of words. The third repetition is how much every pairs of words attends to other pairs of words, and so on. Do you see how monster it becomes after several h's? Assume I repeat it for h times. H is a number of heads, right? So first repetition means how much every word attends to every other word. Second one, how much every pair of words attends to every other pairs of words. The third one, how much every pair of words attends to every other pairs of words, etc. It becomes very a big monster, right? And this measure of attention or similarity between hierarchical pairs of words reminds us of what? Maximum mean discrepancy. What is that? What is maximum mean discrepancy? Do you know that? So for measuring the difference or the difference of two distributions, right? What can we do? The most famous one is that. So I have two distributions. I want to see how much different they are. What is a very famous measure? Scale divergence. I don't know if you have heard of it or not. Scale divergence. Scale divergence. Kullback-Leibniz, I think divergence is its name is hard. So there are two scientists, Kullback and the other one, Leibniz, something like that. In short, Scale divergence. It shows us a divergence or difference of two distributions. First off, it's not a distance because distance must be symmetric and Scale divergence is not symmetric. Okay. And so the more different the two distributions are, the more Scale divergence of them. If two distributions completely match, the Scale divergence is 0. Okay. And another measurement for difference of two distributions is this maximum mean discrepancy proposed by Sholkov et al. Sholkov is the god of kernels in machine learning. He is in Max Planck Institute in Germany. Okay. He has also proposed Hilbert-Schmidt independence criterion, kernel PCA. A lot of kernel methods are proposed by Sholkov. Maximum mean discrepancy is this. Assume I want to compare two distributions. Do you remember every distribution has some modes? First mode, second mode, right? So first mode is what? Can you tell me? First, give me a second, I forgot the name. First expectation, second expectation, that was called mode. I think mode or let's call it mode. As far as I remember, according to my memory. Okay, so expectation of x is called first mode. Expectation of x squared, second mode. expectation of x cubed third mode. Okay. It might be another name, but I can't remember right now. Anyways, I mean this. Okay. What is this? This is mean, right? Right? What is this? This is related to both variance and mean. Recall preliminaries, the formula of variance. I think it was expectation of, if I'm not wrong, expectation of x squared minus expectation of x squared, right? So it is related to variance. What is this? It's related to skewness of the distributions, whether it's like this or it's like this. Okay. So we have infinite number of modes. Oh, I think I remember. It's called, I think, momentum. First momentum, second momentum, third momentum, etc. Now, for comparing two distributions, we need to measure the difference of all of the momentums, right? But it's not possible to do that because we have infinite number of momentums. What should we do? One way to do that is that let's map them to the feature space or to the Hilbert space. In the Hilbert space, calculate their simple Euclidean distance. Hopefully, that calculation is a good estimate of difference of all of the momentums in the input space. Right? This is called maximum mean discrepancy. And this hierarchical pairs of words that I just said has the same idea as maximum mean discrepancy because it's calculating the difference of momentums with each other, right? Anyways, where were we? Okay, we are still in multi-head attention in this module, the multi-head attention. And what do we have? We have queries, values, and keys, right? Right? It is self-attention, right? So do you remember we calculate these matrices of query, value, and key, right? Right? And we do it for h times because of h heads. It's multi-head, right? So as a result, I don't have only one q. I have q1 to qh. I also have v1 to vh and k1 to kh. So I have x's, the same x's as you see. That's why it's called self-attention. I'll calculate all of the w's, the heads, using these weights that I'm having. I calculate all of the values, all of the keys, and all of the queries, the heads, right? And then I calculate the attentions using that formula that we had. Do you remember? The formula of Z, which was V softmax of Q transpose V over square root of P, right? And then we concatenate these Z1 to ZH, right? And so we concatenate, it becomes a very long thing. And then using one linear layer, linear projection, I get Z total, okay? So as I said, we concatenate them. Then using one WO transpose, one linear layer, I get Z total. So far clear? Okay. So this gives me the Z total. Where are we now? We are here. Okay, we are here after multi-head attention. But we have something else that's called add and norm. Do you see that? Add and norm. What is that? Basically, it says, let's add first. So it has two parts, add and norm. Let's talk about add first. What is add? It says let's add or sum the output of multi-head attention with the input of multi-head attention. What does it remind you of? Addition of input and output. What is? We saw that. It's ResNet, right? In ResNet module. So they have been inspired by ResNet. Recall the ResNet lecture, right? Then, so we are using also residual learning here. And then norm. What is norm? This is called batch normalization. Do you remember batch normalization? Do you remember? For reducing the covariate shift. They remove the covariate shift. So what do? After this addition, a layer normalization is applied where they do this. What is this? This is exactly the Z-score normalization that we had also. Minus mean divided by standard deviation, right? So we now where are we? We are here now. After multi-head addition and the batch normalization, then we are here. So here we are here now, and then what do? We have feed-forward layers, right? So the transpose, we feed it to a feed-forward network having non-linear activation function. Usually, even do you remember in convolutional neural networks, we usually have some feed-forward layers at the end, right? So they also have done that, right? Then where are we? We are here. Again, they apply addition and normalization. So they do ResNet, residual learning, and then they do also batch normalization or layer normalization, right? Agreed? So where are we now? We are here now at the end. So we talked about everything in the encoder, and then they stack it for n times. Stack n identical layers. What do I mean? Do you see these? These, they feed it again to this, they feed it again to this, right? N times. Why? Why do they do that? They want to increase the number of learnable parameters because they have a lot of data, internet data. Why not? Let's make the network big, right? To be able to learn. So more learnable parameters. And through experiments, they have found out a good number of stacks is 6, right, in transformers. Okay. Encoder of transformer is finished. Now decoder of transformer. So a part of decoder is the masked multi-head attention module, which is this. We also have positional encoding and distance. Let's start from bottom. So what is this? Outputs or shifted right. So input of decoder here, of course, you might say that the encoder-decoder must be the latent space between encoder and decoder, right? That latent space is here. So you can see this decoder has kind of 2 inputs. One input from the output of encoder, which is here, and this is the output of itself, but shifted, right? Why shifted? Because it's a causal model. It's generating words one by one, right? So it's generating words one by one. Assume we have a sequence, and the next word is generated. Then the sequence becomes larger, so I shift it. I also input that generated output as the next input to it, right? So for example, beforehand it was I am a, and now a student is generated. Then next time I input I am a student to it, right? The previous input was I am a as input. Now the input is I am a student. Then the next word comes and we shift it again, right? So far clear? Now we get the output embeddings using the word-to-vec embeddings, for example, right? Right. Then we again do positional encoding because here we have also order, right? So far clear? Agree? And now we are here, right? Just give me a sec. Yes. Now we are here. Now do we see? So I'm going to talk about this. We have masked multi-head attention. What does it do? First off, multi-head attention, it's multi-head self-attention. Why self-attention? Because query, key, and value are from the same sequence, right? It's self-attention first off. And it's multi-head because it's repeated several times, h times, right? The difference is masked. In encoder, it wasn't masked. But here it's masked. Why? Why is it masked? In the encoder, for example, when we say I am a student in the encoder, assume I'm considering the word a. Okay. It was attending to all the words in the sequence, both beforehand and afterhand, right? So A attendant to I, A attendant to am, A attendant to student, even student when a student is after that, right? Because it was available, it was input, right? But here, I'm generating words one by one. I don't have the future words yet. It's a causal model in the decoder, right? As a result, I don't have the future words yet. So I only should attend to my previous words. That's why we mask it. We mask the future words, right? Mask. So that's one thing. Masks away the forthcoming words after a word, right? Then how do we do this masking? In this way. So do you remember everything here is the same as before, except this plus m. If you drop the plus m, it becomes attention as before, right? But what is plus m doing? It says that if j, so it's a matrix n by n, it's ijth element. What does it mean? When it's attentional, let me think, attentional, the jth word to the ith word, right? Because m is, I mean, this q transpose k, ijth, its element, right? Because q transpose k is n by n. What is its ijth element of q transpose k? Attention of the jth word to the ith word, right? Also, mij corresponding to that attention, I define it as this. If j is less than or equal to I, this should be 0. Sorry, I apologize. The attention of ith word to the jth word, ith word to the jth. Okay. If I is let me think whether ith word to the jth word or jth word to the ith word. Give me a second to think about it. Yes, ith word to the jth word. So when I say ijth, attention of ith word to jth word. Okay. Now consider this. If j is greater than I, what? Yes, I'm correct. So if j is greater than I, this case, what does it mean? I'm attending to a future word, right? Attending to a future. It doesn't make sense. The future word hasn't yet arrived, right? It's a causal model, okay? So I put minus infinity. Everything minus infinity, what happens to it? Becomes minus infinity, right? So the attention minus infinity becomes minus infinity. Softmax has exponential operator. E to the power of minus infinity becomes, guys, in high school we learn e to the Neper number to the power of minus infinity. Minus, oh, e power minus infinity. It means that 1 to the becomes 0, right? So basically this whole thing becomes 0 when j is greater than I, right? But when j is less than or equal to I, what happened? mij is 0. This term is 0. It doesn't have any effect. I still have the attention. So basically, for the attention of my word to the previous words, my ith word to the jth word, which is j, where j is less than or equal to I still have the attention. But for future words where j is greater than I, my attention vanishes to 0. I mask it. Right? Did you see how they did it? Right? They could mask it by programming, by if-else, but they have masked it using mathematics. It's interesting. It's more interesting, right? Now, so this is how they have done it. So masked multi-ed attention. Now, where are we? We are here. Now, what do we do? Again, addition and normalization. Again, we have ResNet learning, residual learning, and batch normalization. Now, where are we? We are here. I'm coming step by step, right? Now we are here, right? Now I'm gonna talk about this part. Multi-head attention. First off, this attention is cross attention. It's not self-attention anymore. So far, whatever we had was self-attention. This one is a bit different. It's query and key comes from output of encoder, but its value comes from the decoder. So as you see, query and key are from another sequence. Value is from another sequence. So they are from different sequences. So it's cross attention. Basically, what does it mean? I have two sequences, two sentences. I see how much every word of this sentence attends to every word of another sentence. You see that? An example, I am a student and its translation in Persian. من یک دانش آموز هستم. Every word in Persian, how does it attend to every word in the input? English, right? So these things. Self-attention was the attention of words within the same sequence. But this is cross-attention, right? So far clear? And what is it basically doing? Basically, it says that how much every word in my output sequence attends to every word in my input sequence. Because query and key are coming from the output of encoder. Agreed? It's interesting. It's interesting. Now, so we talked about this. Then we are here. Now, again, addition and normalization. Again, residual learning and batch normalization. So now we are here. By the way, this is also multi-head attention, right? This is also multi-head attention. Multi-head cross attention. What does it mean? How much every word in the output embedding attends to every word in the input embedding. Also, how much every pair of words in the output embedding attends to every pair of words in the input embedding. Also, how much every pair of pairs of words in the output embedding attends to every pair of pairs of words in the input embedding, and so on. It becomes a monster, right? Then what do we have? Again, several layers of feed-forward neural networks with the nonlinear activation functions. Then we also, again, have residual learning and batch normalization. So far clear? As I said here. So now we are, by the way, this is also repeated n times. Again, put them back to back as before I explained it to you. Similar to what we had in encoder, right? Why? To have more number of learnable parameters, because we have the whole internet data corpus to train, right? For example, we have the whole Wikipedia. Wikipedia is a very good corpus for training natural language processing. They use Wikipedia plus every other word, many other websites. I believe they have used Twitter as well. That's why Elon Musk wanted to sue them, right? They use a lot of platforms, including Twitter, Wikipedia, etc., right? And why is Wikipedia useful for training? Because it has different subjects. It has material for sports, for politics, for philosophy, for psychology, for mathematics. It has different subjects. Okay, so where were we? With repeated n times. Now we are here, right? What is this? Linear layer. Now we have a linear layer, a feed-forward neural layer, dense layer, right? Then we use softmax activation function. By the way, how many neurons do we have at the output? Because this is output of decoder, right? Where I have softmax activation function at the end. How many neurons do I have at the end? What is my output for decoder? It's the output probabilities of the words. Can you guess how many neurons do I have at the end of the decoder? Give me your guesses. If it's that's wrong, that's fine. Do I have 10 neurons? Do I have 100 neurons? How many neurons do I have? 2 neurons, 5 neurons, 10 neurons, 100 neurons. How many do you? What determines the number of neurons at the end? Give me some guess. How many words do we have in the dictionary of English? Or assume we are training for this for English. What? 1,500? I don't know, maybe. A lot, right? A lot. So the number of neurons at the output layer of the decoder is the number of words in that language, the number of words in the dictionary. If it is English, we are training for English, the number of neurons should be the number of words in English. If it is Chinese, the number of words in Chinese, right? So of course it becomes very huge. And why do we use softmax? Because we want to calculate the probabilities of the next word, the probability of the next word. We know that when we use softmax, it becomes like probability and they sum to 1. And then one of them at least becomes larger than the other one, the probability, right? That will be the next word, right? Although I believe that the probabilities become very small because the number of neurons is very large. The probabilities are very small, but one of them is still larger than the other ones, right? That will be the next word. So what word is the next word with the highest probability, right? For example, assume here as the input I had, I am a student, and what should I say? For example, as input I have this Persian words. من یک دانش آموز هستم. I want it to be a translator, okay? And so the input is this, the output, for example, was I am a, the next word. Now I calculate the probabilities. So the largest probability is a student with maybe probability 0.0001. Although it's a small probability, but it's larger than all of the other probabilities, right? Maybe the next one was a teacher, because teacher is related to a student, but its probability is less than that, maybe 0.009, right? But student wins because it's larger, right? And becomes the next word. Do you see the beauty? And then this word comes as shifted input to the decoder again, okay? So far clear? Now let's talk about complexity of attention. First off, attention is all we need, as I said. The output of decoder is fed to the masked multi-head attention module, do you remember? Of decoder with some shift, right? And this is not a notion of recurrence. We see that there is not any recurrence module like recurrent neural network or LSTM. We don't see something like this that we had in previous, where we unfolded that it becomes like this. Do you remember? We had that in the lecture of the previous lecture. That was recurrent neural network, but we don't have such recurrence here. As a result, attention is all we need to learn a sequence, and there is no need to any recurrence module, okay? This proposal of transformers was a breakthrough in natural language processing. It revolutionized NLP, okay? Nowadays, mostly in NLP, they use transformers, BERT, GPT, etc., right? Attention. Nowadays, they usually don't use recurrent neural network and LSTM. They are outdated, kind of. So the state-of-the-art NLP methods are based on transformers nowadays. Even some professors have removed recurrent neural network and LSTM from the outline of their courses. For example, Professor Ali Qudsi completely removed them. So it's irrelevant, it's outdated, okay? So in self-attention, let's compare the complexities. In self-attention, we learn attention of every word to every other word in the sequence of the n words, right? Because do you remember? In self-attention, we learn attention of every word to every other words. We also learn a p-dimensional embedding for every word, right? P-dimensional embedding for every. As a result, the complexity of operations per layer is O n squared p. O is a big O notation in complexity. N squared because n words, each word attends to every other words in the sequence. And p is because I have p-dimensional embedding per word, right? But complexity in recurrence without proof accepted from me, that is O n p squared. So in recurrent neural network, this is O n p squared, but in attention is O n squared p. Okay. Although the complexity per layer in self-attention is worse. Can you compare these two? Which one is worse? Usually n is larger than p, I believe, right? That's why O n squared p is worse than O n p squared, right? N is the number of words, right? So you might say attention became worse in terms of complexity. Yes, but there is a but. We can do it in parallel because all words of the sequence are processed simultaneously. When you calculate the attention of this word to the other word, you can also at the same time calculate the attention of this word to that word, right? They are not dependent on each other in terms of attention. So you can do it in parallel, but in recurrent neural network, you can't do that because you need recurrence, right? You need to feed the output again as input. For going from one word to another word, you need to do the recurrence between them, all recurrence between them. So it cannot be parallelized. As for the number of sequential operators, the self-attention mechanism processes all the n words simultaneously. So its sequential operations is in the order of O1 because there is no sequential recurrence in it, right? But in recurrent neural network, it's ON because it's sequential. For going from one word to the other word, you need to pass through all of the words in between, right? Also, what about maximum path length? Again, in attention is O1 because you have attention of every word to every other word directly, right? But in recurrence is ON. Again, you need to pass through the whole words between them, right? Big O notation is the worst case scenario. You know that it's upper bound, right? That's why it's ON. So now we have summarized these things. As a result, in these two cases, attention is better. In this case, where attention is worse, but it's not a big issue because it can be done in parallel. Now we have talked about attention, transformers. Now let's talk about BERT and GPT. So what is BERT? BERT is short for bidirectional encoder representations from transformers. Okay. It's one of the state-of-the-art methods for NLP. What is it? It's nothing but a stack of encoders of transformer. So do you remember transformer that we talked about? It was an autoencoder. It had an encoder and decoder. If you drop the decoder and only have encoder and you stack the encoder several times to become larger, they call it BERTs. If you drop the encoder and only have the decoder and stack it several times, then it becomes the GPT, okay? So BERT is encoders of transformer and GPT is decoders of transformer. So as I said, it's a stack of encoders and it's using transformer encoder blocks. Although some NLP methods such as XLNet have slightly outperformed it, but BERT is still good, especially for question answering. So these are different tasks for natural language processing. Question answering is that you give a question, it answers for you. So how do you train it? You train it using question answer pairs, right? Another one is natural language understanding, understand that what text is about. Sentiment analysis, whether for example, the emotion of the text, whether it's hateful or not. For example, YouTube uses that for removing the hateful comments, right? Well, whether the comment says that the customer likes the product or not, something like that. These are sentiment analysis. And language inference. Anyways, BERT uses the technique of masked language modeling. What does it do? How do they train BERT? They use masked language modeling. What do I mean? How do they prepare the data for training BERT? Do you know that? So they say they get the corpus, then in some word, in some sentences, they randomly mask one of the words in the sentence, right? In the middle of the sentence or at the start or at the end, doesn't matter. Randomly, they take one of the words and mask it, and we have the other words. Now they say, given the other words in the sentence, I need to predict the masked word, right? That's called masked language modeling. So basically, they have the whole internet data. By the way, what is corpus in natural language processing? The text that you use for training is called corpus, right? It's written as this, corpus. C-O-R-P-U-S. Okay, where were we? So it masks 15% of the words in the input document or corpus and asks the model to predict the missing words, right? A sentence with missing word is given to every transformer encoding block in the stack, like this, right? And the block is supposed to predict the missing word. For example, here, the sentence Mona Lisa is a portrait by Leonardo da Vinci. Give it to transformer encoder, it gives Mona Lisa. Also, if you mask portrait, it gives portrait. If you mask Leonardo da Vinci, it gives Leonardo da Vinci, right? And it is a stack of transformer encoders, as you see. Now, as you see, it is an unsupervised learning. Why? Because we can mask anything, right? You don't need labels for it, right? You give me some corpus, I mask several words in it randomly. So it's an unsupervised. When it is unsupervised, it means that we don't have to have any effort for making labels. Therefore, we have a lot of data. Making label is a big issue in machine learning, and it is very costly, expensive. You need to pay people to make labels for you. But when it is unsupervised, it's easy. So you have huge text of internet data, right? Okay. And as you can mask anything, such as a word in the middle of a sentence, what is it doing? Conditioning on the previous words and the forthcoming words. What is this? As a result, it's a bidirectional model. Bidirectional embedding, right? Given the previous words and the next words, what is this word? Do you see that? Do you see that? That's why it's called BERT. The B in BERT is standing for bidirectional, because it's bidirectional one, right? Do you see that? So jointly conditions on both left, previous, and right forthcoming word. Okay. Moreover, it is a context-aware embedding. Again, because it's conditioning on the words, on the other words in the sequence. As a result, it will have different embeddings for the two banks in these two sentences. Vegetation in the bank of river and money is in the bank. These two banks are different because the context is different, right? So it's context-aware embedding. By the way, in parentheses, let me tell you that this part, the context-aware embedding, as well as attention mechanism, is also related to philosophy of language. In parentheses, let me tell you this. A century ago, there was a mathematician slash philosopher named Gottlob Frege. Okay. By the way, do you know that function in mathematics is proposed by Frege, who was a philosopher slash mathematician? It's interesting. So when you read Frege's papers, you don't know whether you are reading a philosophy paper or a mathematics paper. It's not obvious. Okay. So he proposed that, and where were we? So I said he also proposed something named context principle. It's very famous among philosophers, analytic philosophers. They know about it. Context principle says that the words in a sequence are aware of the other words in the sentence. Otherwise, the words care about the context of the word of this sentence. For example, when you are talking to a car dealer, you use different words than when you are teaching in the class. Right? So the context is important for choosing the words, these things. And as you see, after a century, after 100 years, we are doing that in machine learning. Attention says that every word attends to every other word. Also, we have context-aware embeddings. It's important that which context this word is used in, right? The word bank, whether in this sentence or the other sentence, it will have different meaning, right? So that's also related to philosophy of language. I believe that natural language processing in machine learning is closely related to philosophy of language or linguistic philosophy in philosophy. And it is started 100 years ago by Gottlob Frege, Bertrand Russell, and Ludwig Wittgenstein. Also, some other people have continued that, such as Quine and Kripke. These are also very famous analytic philosophers. Okay, where are we? So, by the way, for more information on the relation of philosophy and mathematics and machine learning, feel free to read one of my latest papers on philomatics and psychomatics for combining philosophy and psychology with mathematics. Okay. So, by the way, some other techniques such as word-to-vec and glove, they were not context-aware embedding. For those two sentences, if you use word-to-vec, it will give you the same embedding for the word bank in the two sentences, although they have different meanings. So that's a flaw of non-context-aware embeddings such as word-to-vec. And yeah, different BERT embeddings in various sentences. An examples are money in the bank and some plants grow in the bank of rivers. Okay, so BERT outputs an embedding also for the whole sentence. In addition to every word, it has also some, now this part is practical. In practice, I'm saying that. It also outputs an embedding for the whole sentence, in addition to giving embeddings for every word. Although it's not perfect, but it works well. Usually, for example, people have used that for spam detection. So you can do various things. Either you take the embedding and you use a simple classifier on the embeddings as the features, or you can fine-tune your BERT by transfer learning. What do you do? For example, you can freeze some of the initial layers of the BERT and only fine-tune the last layers of the BERT. Or you can add one or more the neural network layers on top of a pre-trained BERT and then freeze the weights of BERT and only tune the weights of additional layers, right? Fine-tuning. You can also fine-tune BERT weights as well. But we usually use pre-trained BERT and fine-tune it. We don't train BERT from scratch, right? Because BERT has been trained on the whole internet data for months on big servers. We can't do that on simple PCs, right? Okay, the parameters of encoder in transformer are, and these are the parameters: 6 encoder layers, 512 hidden layer units in the fully connected network, 8 attention heads. Do you remember? In regular transformer, we had 6 attention heads. They have used 8 attention heads, right? So, no, by the way, sorry, these are in, I apologize, these were in transformer, 8 or 6. But BERT has used a lot more, 24 encoder layers, 124 hidden layer inputs, and 16 attention heads. Whatever transformer uses 8 or 6, doesn't matter. BERT uses much more. Why? Because they want to have more learnable parameters. And also they want to make it stronger. So attention of more hierarchies of pairs to more hierarchy of pairs, right? Usually when we say BERT, we mean large BERT, reference 36, right? Which has these parameters. But there's a problem. How can we have BERT in the embedded systems, such as cell phones? We can't, because we'll have memory error. It doesn't fit in the memory, right? As a result, they have made smaller versions of BERT. So small BERT, tiny BERT, distill BERT, Roberta BERT. These things, they're different versions. By the way, BERT, do you know that BERT, these models are very useful for cell phones. Why? Because natural language, it can use natural language processing. You can talk to Siri and it writes something for you, right? You might say something and they want to convert it to text or whatever. You write something and you say translate it. Phone can do a lot of things with NLP using BERT, for example. That's why BERT has been used a lot in cell phones, and many big cell phone companies, I don't want to name them here because it's been recorded, many big ones are investing on using BERT. Okay, and how do they make these tiny or these small BERTs? Do you know that? They use a technique named network compression. One of the important techniques for network compression is knowledge distillation. What is knowledge distillation? It says this: consider a big network, right? You want to make it a small network, right? So consider a big network, we call it teacher network. And a smaller network, we call it a student network, right? So we want to distill knowledge from the teacher network to the student network, right? What can we do? We can, again, several variants. Either we don't train teacher, we use a pre-trained teacher and we only train student, or we can simultaneously teach the teacher and the student together, right? Doesn't matter. So for teaching each of them, first off, whatever loss function we use for a teacher, we can use for a student as well, right? That's one thing. For example, I don't know, cross entropy, whatever we use, for example, for the decoder of the transformer, we can use cross entropy on the softmax, right? Whatever you use, whatever loss function that you use for training your network, you do that for the student as well. But there is a but too. The loss of the student is not just that loss. It's regularized by another loss. I mean, it has two loss functions added together with some weight, right? With some regularization parameter. The second part of the loss in the student is imitating from the teacher. So the teacher outputs something. The student is a slur. Teacher outputs something, a student outputs something. I have L1 on this, loss one. Also have loss one here. But I also have loss two. So with some weight, I have also loss two. What is loss two? Imitating to output here. So loss two is basically, so assume it output is Y teacher, output of a student is Y student. It can be the mean squared error of Y teacher and Y student. Y student should be similar to Y teacher. Do you get it? So now this is distillation. And again, different variants. So it's a family of methods. Now you tell me, what if teacher is too large and the student is too small? Assume your manager in your cell phone company says, assume you work in a cell phone company, your manager comes to the AI team, says, if we don't have enough memory, make it too small. Okay, but BERT is too large. Then this distillation might not work well. What do? They add a third network in the middle called TA network, teacher assistant. Teacher assistant network, okay? Which is, its size is between teacher and student. So it helps to with distill knowledge from teacher to teacher assistant, and then from teacher assistant to the student. As you see, we can have a hierarchy so you can have teacher assistant 1, teacher assistant 2, teacher assistant 3, and then a student. We can have a hierarchy as well, like a pyramid, right? Do you see that? So this is a technique that they use, one of the big techniques that they use for compressing networks. Anyway, some BERT models such as clinical BERT and bio BERT have been, we can have BERT for a specific domains such as medical domains, medical texts, prescriptions, prescription analysis. So they have trained BERTs for these applications, and they have named it clinical BERT, bio BERT, right? We even have BERT for genes, as you can see gene as a sequence of amino acids or residues, right? GPT. GPT is short for generative pre-trained transformer. Okay. The first GPT was GPT-1, reference 47. It's another state-of-the-art method for NLP. It was proposed by OpenAI. Okay. Initially, it was open. Now it has become closed. Okay. So what is it? It's basically saying that only consider the decoder transformer and stack it several times to become bigger, right? So a stack of decoders of transformer. In other words, it is built using transformer decoder blocks. Again, in GPT, do you remember the decoder of transformer? We had multi-head self-attention. We also had multi-head cross-attention. Do you remember? Now in GPT, we have removed the encoder of transformer. We don't have encoder. How can we work with the multi-head cross-attention? Because multi-head cross-attention needs to calculate cross-attention between the sequences of the decoder and the encoder, but there is no encoder now. As a result, they completely removed the cross-attention module. Okay, so they have decoder, the cross-attention is useless, removed. Okay, they only have, but still they have attention. They have multi-head self-attention only, right? So we have positional encoding, masked multi-head self-attention, and feed-forward, and those addition, residual learning and layer normalization, batch normalization, right? And the activation functions. And GPT uses masked multi-head self-attention. Do you remember? So it masks the future words because it's a causal model, right? Agreed? So it only conditions on the previous words, right? In attention. As a result, it's not bidirectional. As a result, the tasks of BERT and GPT are different. The task of BERT, what was it? You don't have some word somewhere in the sentence, maybe at the start, in the middle, or at the end. Given the other words in the sentence, what is the probability? What is this word? Let's predict this word. It's bidirectional. But GPT is complete. Its task is completely different. It says that given the previous words, what is the next word? So that's why it generates word by word, one by one. So assume it wants to write some text for you. It makes the first word, then given the first word, it makes the second word, then given the first and second word, it makes the third word, and comes and continues the text. That's why ChatGPT works like this. ChatGPT is a GPT model, right? As you see, it generates words one by one, especially when it came first. Nowadays, it has become fast. Initially, when it was released, it was slow. You could see that it generates this word, then after 1 second, generates the second word, then the third word, word by word, right? But now it has become fast that you might not notice. Okay, so it generates word by word. That's one thing. As a result, it's not bidirectional. Conditions only on the previous word. Also, do you remember in the decoder of transformer, we had shifted output as the input of decoder as well, again, right? As a result, it always remembers the previous words, right? That's why when you chat with ChatGPT, For example, at the start of the conversation, I say, hey, ChatGPT, I am Benjamin. How are you? Then I talk to ChatGPT for a few minutes, right? I chat with it. And I say, by the way, do you remember what was my name? It will say, yes, your name is Benjamin. How could it remember that? Because of this shifting. You're always shifting the output as input again. So it always remembers the previous things. Of course, with some memory limit, with some window, right? Is it obvious? It's interesting. So the objective of BERT was to predict a masked word, but this, however, GPT is a language model. What does it mean? It generates text for you, right? Predicts the next word in an incomplete sentence, given all of the previous words. As a result, GPT is a causal model, but BERT is not a causal model. Predicted new word is then added to the sequence and is fed to the GPT as input again. Exactly what I said in a few minutes ago. Okay. In other words, GPT model takes some document and continues the text, right? That's why if, for example, you give a paragraph to ChatGPT and say continue it, it can continue. Given this paragraph, let me generate some other text related to that. And as you see, still, it is an unsupervised model. Why? For training that, they can use the whole internet data. Why? Because you can always take some paragraphs from Wikipedia or whatever in internet and say, this is the paragraph, this is the next word. These are the previous sentences, and this is the next word. So you can generate training data easily. Given 3 sentences ago, this is the next one, right? So you can use a huge amount of internet data, such as Wikipedia, such as Twitter, etc. The successors of GPT-1 were GPT-2 and GPT-3. Nowadays, we have GPT-4 too, right? GPT-2 and GPT-3 are extensions of GPT-1 with more number of stacks of transformer decoders. So they made it larger and larger because they wanted to train more with more data, more learnable parameters, right? We are in the era of big data. That's why we need a lot of parameters to learn, right? GPT-2 has 1.5 billion parameters. What do I mean by parameters? Weights, neural network weights, right? 1.5 billion. GPT-2 and especially GPT-3 have been trained with much more internet data with various general and academic subjects, different subjects, right? To be able to generate text in any subject and any style, right? For example, GPT-2 has been trained on 8 million web pages, which contain 40 gigabytes of internet data. Text, text data is usually not memory consuming a lot, right? It's usually kilobytes. Now you can imagine how much text is 40 gigabytes. Okay. GPT-2 is quite large and cannot be easily used in embedded systems, of course. Again, like, do you remember we had a small BERT? We also have a small GPT. We have a small, medium, large, X large, and distilled GPT-2, different variants, right? And by the way, you can find many of the versions of GPT-2 in Hugging Face Transformer Python package. What is Hugging Face? It's a library for natural language processing in Python. Many of the GPT, BERT, and these things can be found in Hugging Face. Okay. GPT-2 has been used in many different applications, such as dialect systems. You have a dialect. Patent claim generation. Called text simplification. Also, we can combine GPT and BERT. For example, for question answering, you can see these references, right? Also, some papers have said you can see it as few-shot learning. What is few-shot learning? Its name is obvious. It means that using a small training data, how can I generalize well? So let's not use very big data. Let's use only few shots, few number of training points per, for example, class, and let me design a model where it only needs few number of data points, data instances to be trained. Okay, that's called few-shot learning. By the way, one of the ways for few-shot learning is called meta learning. Meta learning is is learning to learn. How to learn to learn. Okay. A comparison of BERT and GPT can be found in reference 58. GPT-3 is a very huge version of GPT, so with so many number of stacks and learnable parameters. For comparison, let's compare them. GPT-2 has 1.5 billion. NVIDIA Megatron has 8 billion parameters. Microsoft Turing NLG, these are NLP models for different companies. It has 17 billion. GPT-3 has 175 billion parameters. That's why ChatGPT works very well. Okay. And this huge number of parameters allows GPT to be trained on very huge amount of data, right, with various subjects. It has learned almost all topics. By the way, some people say that it has kind of memorized internet data, but in a good way. Memorization in a bad way means overfitting, right? They say it has memorized, but not in an overfitting way, in a good way. This is what they are saying nowadays. Also, some people are saying that it is passing Turing's writer's test. What is Turing's test? Have you seen? Have you heard of this? Turing's test says that Alan Turing said that let's have a test to see whether AI can beat human or not. For example, randomly we select either a human or a computer generate something, and then we give it to some human subject to can that human judge whether it's made by a human or a computer, right, or a machine. Then apparently it is passing Turing's test, saying that we cannot find out whether it's generated by GPT or human. Okay, it can generate even Shakespeare's poems. You cannot find out whether it's Shakespeare or machine. So kind of memorize in a good way, not overfitting. Complexity, so it has huge number of learner parameters. Big enough internet data is required not to have overfitting, right? So as they have trained on big data, they haven't overfitted. Otherwise, they would overfit, right? Because they have made the network very big, so they also need a lot of data to train it. And also it has been used for fiction and poetry generation. Acknowledgements. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi and Professor Pascal Poupard at the University of Waterloo. And this lecture is based on our tutorial paper, Attention Mechanism Transformers, BERT and GPT Tutorial and Survey. Feel free to see that. By the way, Archive rejected this paper. I put it in another preprint server. Okay. So these are the references. It has a lot of references. I go through the references for these to be recorded because we cited them in the lecture. Okay. Any question? No? Let's have a break and come back at 9, and then we'll continue the session. Yeah. Thank you. Okay. So now we continue with deep metric learning. Okay. Some people left, I guess. Okay. So deep metric learning. By the way, the sequence processing is finished with deep learning. We talked about it. Now we move on to other topics. So metric learning can be divided into three parts: spectral metric learning, probabilistic metric learning, and deep metric learning, or neural network based deep metric learning. What is spectral and probabilistic? So these spectral and probabilistic metric learning, they use generalized Mahalanobis distance. What is generalized Mahalanobis distance? So let me talk about the Mahalanobis distance first briefly. So consider these two clouds of points. Yes, and a test point here. So by the way, a cloud of points, I mean a lot of points here, right? And mean is here. The mean of this cloud of point is here, right? Using simple Euclidean distance from the means of the classes tells us that this test point belongs to class 1 because this distance is shorter than the other, right? But our visual system says that it belongs to class 2. So clearly Euclidean distance is making a mistake here, right? As a result, let's rescale these distances using the scatters of the classes. As you see, a scatter has, if we consider the scatters, then this mistake can be resolved. This is exactly what Mahalanobis did. Mahalanobis was an Indian mathematician. We have at least 2 very great Indian mathematicians in previous century. Who are they? One of them is Mahalanobis, who was a statistician. The other one was Ramanujan, who was a scientist in number theory. Okay, and they met in UK, I think in Cambridge. They met with each other. So Mahalanobis said, let's rescale them in the way that rather than using xi minus mu times xi minus mu, what is this, by the way? This is exactly the Euclidean distance between xi and mu. Mu is the mean of the class, right? We calculate this twice, right? Once for this and once for this distance. And this is the squared. This is a Euclidean distance, right? Sorry, this has the transpose here, right? But Mahalanobis says, let's add sigma inverse in between, right? Why? Where sigma is the covariance matrix of each of these classes, right? So why do we use sigma inverse? Because the bigger the covariance, the scatter of data, the smaller the distance should become. That's why sigma inverse is used, right? And this is Mahalanobis distance. Later, people said, why do we use Mahalanobis distance? We can generalize it better. We can say xi minus mu transpose, which matrix have I used here? W xi minus mu, where W is any matrix but with some properties. W must be positive semi-definite, meaning that its eigenvalues must be all non-negative, either greater than 0 or equal to 0. Why? Because it needs to be a distance metric, right? Distance. What is recall preliminaries? What are the properties of the norm? Because norm and distance are related to each other, right? One of them was triangle inequality. For this to satisfy triangle inequality, it needs to be positive semi-definite. Also, for this to be convex, it needs to be positive semi-definite W. So this, we call it generalized Mahalanobis distance. And then in metric learning means distance metric learning. Let's learn the metric. What can we learn in a metric? This W, right? So it's basically saying that let's learn this W, and we know that all machine learning is optimization, right? So we have some cost function using this generalized Mahalanobis distance where the optimization variable is this W, for example, right? How do we find this W so it does what we want? For example, separation of classes, right? Or if we don't have classes, how do we push the similar points to each other and pull away the dissimilar points, right? So this is, I'm saying that we can find this W using in optimization. Where were we? Okay, so this is exactly what I defined. Generalized Mahalanobis distance, and it's a squared is this, right? The deep metric learning, however, is a bit different. It doesn't use generalized Mahalanobis distance. It says let's learn and embed in a space as the output layer of the neural network, in the output layer of neural network. In that case, I want in the output or one to the last layer of neural network. Doesn't matter. So I want to learn some space where these classes are separated in supervised case. If it is unsupervised, where the similar points fall close to each other and dissimilar points fall away from each other. Okay, this is deep metric learning. So discriminating classes or dissimilar points and making the similar points close to each other, right? And any distance metric can be used for learning this embedded space in the as a loss function, for example, such as a squared L2 norm or a squared Euclidean distance, right? F here is what? Xi is the input. F of Xi is the output of neural network for the input Xi. Okay, assume my neural network has p number of neurons at the end. That as a result, f of Xi is p dimensional, and then I can calculate the distance between f of Xi1 and f of Xi2, 2 points, right? That's one thing. And we have some learnable parameters, theta, the weights of the neural network, right? We can also learn by mini batches. Recall that lecture about stochastic gradient descent, right? We said that we can have mini batches. So far clear? Okay, now let's talk about reconstruction autoencoder. By the way, I will tell you some examples of some example algorithms for deep metric learning. We will see that. So reconstruction autoencoder. First off, reconstruction loss. We denote the input data point to the encoder by x d-dimensional, where d is a dimensionality. So consider some autoencoder where I have encoder. We also have decoder. I have x, and also I have x hat as the output of decoder. X hat needs to be as close as possible to x. Hence, this autoencoder is called reconstruction autoencoder. It needs to reconstruct x as its output. And here I have latent space. As you see, latent space here is compressed version. That's why finding x hat from x is hard. Why? Because it needs to pass through some bottleneck. Compressed bottleneck. Do you see that? Do you see that? Okay. So an x hat is the d of f of x or d of e of x. By the way, f of x here is the output of encoder. So f of x is our latent embedded in the space, in the latent space. Latent embedding vector in the latent space. Here is latent space, right? Compressed latent space. P dimensional. Where P here is usually less than D. If P is less than D, it's called undercomplete autoencoder, like this, right? If P is greater than D, then it means this. It's called overcomplete autoencoder. But overcomplete autoencoder, if I have X as input and X hat as output, it becomes trivial. Why? Because if you use backpropagation, it will learn the ways to simply copy. It simply copies, right? Because you don't not only you compress, but also you have more number of neurons in the middle, so you can simply copy. So many of the weights will be 0, and some of the weights will be only 1, for example, or something like that to copy. It will learn to copy. But the thing is that overcomplete autoencoder has some use cases, especially it's used for denoising. So usually denoising autoencoders are overcomplete autoencoders. What do I mean? So rather than x, I input x plus noise, epsilon, but I output x hat. So I don't reconstruct x plus epsilon. I reconstruct x. As I input, I have x plus epsilon, corrupted data, but in the output, I have x hat. So as a result, X hat is the denoised X, right? Denoised data. In this case, then it cannot copy anymore because I have plus epsilon in the input. So, for example, I can use this loss function. This is summation over the batch, right? And this is the distance between xi and xi hat, plus lambda is the regularization parameter, and this is the regularization term. Omega theta. Omega theta is some regularization term, some penalty, right? We talked about it in the regularization lecture, right? Recall that lecture. This distance can be, for example, a squared Euclidean distance. If we use a squared Euclidean distance, this is called mean squared error, because it's mean squared error. Error is the distance. Mean is because it is mean, right? Kind of mean. It's a scaled mean. 1 over b summation becomes mean. And error, so squared is because it's squared Euclidean distance. A problem with overcomplete autoencoder is that it's training only copies, as I said, but we can use it for denoising. In other words, the network memorizes or gets overfit, right? If it is overcomplete without any noise. So we add some noise for denoising. And it's called denoising autoencoder, as I said. DAE. Okay. Under complete reconstruction autoencoder, usually P is much less than D. So we compress a lot. Okay. And it's used for metric learning. It's used for dimensionality reduction because we are reducing the dimensions from D to P, right? So you can see the embedding vector in the latent space as a dimensionality reduced data, right? So in the middle, I have embedding space, right? In the embedding space, I can do anything. For example, if I use, so reconstruction autoencoder, its loss, for example, is mean squared error, right? But I can add some other losses as a regularization term. For example, separation of classes in the embedding space. So basically, encoder, decoder, x hat, my loss can be x minus x hat is Euclidean squared plus lambda, assume this is f of x, some loss on f of x. So my loss gets both the output of decoder and output of encoder in it, right? And this loss can be the loss for separation of classes. You see that? If I train this, then in my embedding space, the classes become separated. In addition to reconstructing data by the encoder and decoder, right? That's one thing. And also, as I said, you remember I said if you don't use any nonlinear activation function, all of your layers become reduced to one layer, to one linear projection. And if you don't use any activation function, your reconstruction autoencoder becomes principal component analysis, PCA. Why? Because do you remember go and see my lecture on PCA in my statistical machine learning course. One of the formulations for PCA is minimization of reconstruction error. So you can see that PCA is the linear algorithm which minimizes reconstruction error, the linear algorithm. When you don't use any nonlinear activation function in your neural network, it becomes a linear algorithm. As a result, backpropagation will learn whatever PCA directions are. Okay, so your encoder becomes linear projection onto the PCA subspace. Your decoder becomes a reconstruction from the PCA subspace. Okay, if you don't use any activation function, as a result, you should use nonlinear activation function for this to be a nonlinear model. Okay. Nonlinear neural network can be seen as an ensemble or concatenation of dimensionality reduction and kernel methods. Let me tell you this. Consider, I already have talked about it briefly before, but let's say it again. Remember, if we have a neural network, from every layer to another layer. Either the number of neurons reduce or increase, right? If it decreases the number of neurons, then it means that we are doing dimensionality reduction. If we have activation function, we also have nonlinear dimensionality reduction. Without activation function, it's linear dimensionality reduction. Okay. If we go from lower number of neurons to higher number of neurons, it means it's like kernel methods, because in kernel methods, we increase the dimensionality usually, right? So as you see, we have a bunch of layers, right? So you can see a neural network as a stack of different machine learning algorithms. That's why it becomes a monster, right? But so yeah, kernel methods map data from input space to the reproducing kernel Hilbert space. For more information on reproducing kernel Hilbert space and kernel methods, see my statistical machine learning course. Okay. So yeah, each layer of neural network learns its own features from data. And as you see, it's an ensemble learning because they cooperate with each other. The different layers cooperate with each other. And it's interesting that for example, some layers say, I extract these features, therefore the other layer will not extract those features. They don't become redundant. They will learn another type of feature. And that's interesting. So it's like they are cooperating. By the way, when you train neural network, convolutional neural network on images, usually when you look at the features, initial layers, as far as I remember. So last layers become very like different, capture different parts of the image. For example, the different coarse parts of the image, but initial layers become very features such as sine and cosine. And it becomes kind of similar to sine and cosine patterns. They are called Gabor filters. Have you heard of Gabor filters? Let me Google it for you, so you see its figure. Gabor filter. It's like this. It's an exponential operator carried on some sine and cosine. Okay, with some degree angle, and these usually appear a lot in the initial layers of neural networks. Gabor is written as this, Gabor filter. You see that? Gabor filter. And by the way, it has been seen that the cells in our eyes have Gabor filters. So it's basically backpropagation will learn in its initial layers. What it will learn is similar to what we have in our human visual system. Very interesting. Okay. So supervised metric learning by supervised loss functions. So supervised loss functions can teach the network to separate classes in the embedding space. So now it's supervised, we have class labels, so we can separate classes, right? We don't want classes to be confused with each other, right? So for this, we use a network whose last layer is for classification of data points. So consider this neural network. We usually have a backbone network, which can be any network, such as ResNet or fully connected network, whatever. And we usually have one last layer as classification layer, right? The output, for example, we use some classification loss, such as cross entropy, right? But one to the last layer, we call it embedding layer, okay? When we use a classification loss, at the end, usually in the embedding layer, the classes become very separated from each other. If you visualize the points in the embedding layer, of course, this embedding layer, for example, is assumed 40-dimensional. You can't see 40-dimensional. You apply t-SNE or UMAP on this 40-dimensional space to visualize it in 2-dimensional space. t-SNE and UMAP are non-deep learning or a statistical dimensionality reduction algorithms. They are probabilistic, okay? They are used a lot for visualization of features in neural networks as well. So you can visualize them using UMAP or t-SNE or t-SNE to visualize them in 2D, 2-dimension, and you see that the classes have been separated because of that classification loss. So as I said, I already explained these things, right? So we have fully connected layer at the end. We can use, it can be feed forward or convolutional, but usually it's feed forward because here, what are the number of neurons at the end? The number of classes, right? And we usually use softmax activation function, right? We call the lectural activation function. And this embedded in a space usually extracts discriminating features for discriminating the classes. So one of the supervised loss functions is mean squared error. When is it used a lot? When the labels are continuous, used for regression. So mean squared error is usually for regression because you want to reduce the error of between the continuous labels, right? Another one is mean absolute error, which uses this. Sorry, this is L1 norm, right? L1 norm. This is L2 norm. This is L1 norm, right? And this is mean, again, this is also for regression. Both of them are for regression. By the way, L2 norm is also called Euclidean distance. L1 norm is also called Manhattan distance. Why? Because it's like, assume you are in a Manhattan city, and for going from one point to another point in this city, you need to go through the streets, and the streets are like this. They are not like this, right? It becomes L1 norm. Where were we? By the way, let's compare mean squared error and mean absolute error. So mean squared error has one advantage over mean absolute error. Is what? L2 norm, in other words, has one advantage over L1 norm. It's differentiable. It's a smooth. But L1 norm is not as smooth, especially in the origin, right? This is L1 norm. It's not as smooth here. What about advantage of L1 norm over L2 norm? L2 norm has one big flaw. And what is that? This square exaggerates outliers. If you have an outlier, it becomes larger, right? But L1 norm doesn't do that. In other words, if you draw L1 norm and L2 norm, this is L2 norm, this is L1 norm. L1 norm is not as smooth, a problem of L1 norm. But now consider an outlier. Its L2 norm is very big. Its L1 norm is not that much big. Because L2 norm has a squared in it, right? So they have pros and cons. By the way, L1 norm in neural networks is not a big issue. Why? Because we usually calculate derivatives numerically. What do I mean by numerically? Do you know what I mean? It's important. Let me talk about it briefly. Derivative of x1, x2, x3. This is a vector x with respect to y1, y2. How do I calculate this? Using the definition in high school. Numerically, I want to calculate them. You know that? So what is the definition of derivative in high school? If I change y, how much does it change x, right? So basically it means that for now I need to do it element-wise, right? So basically it says, let's for simplicity, for now, assume y is just a scalar. Assume for now. Okay. Then it says that change y a bit and see how much x1 changes. Of course, x2 also changes. x3 also changes, right? So this is and then what should we do? So we had before and after, like before and after in surgeries, x1, x2, x3. You can compare these two, right? What was definition of derivative f of x plus delta minus f of x over delta limit delta goes to 0, something like that, right? So I think now in our case, let me denote it by another notation. So in our case, the derivative becomes, let me think, x1 plus delta 1 minus x1. So the numerator becomes delta 1 over epsilon, where epsilon goes to 0. What do I mean? Epsilon is a small number. For example, epsilon is 0.0001. So basically they approximate it by 0.0001 over delta 1. This is numerator. So that, what is this? The first element of this, because this becomes a vector, right? A three-dimensional vector. This is the first element. The second element will be delta 2 over 0.001. The third element will be delta 3 over 0.001. Now also you can calculate the same if y is also a vector. If x is a vector, y is a vector, delta x, derivative of x with respect to y becomes a matrix, right? So this is how they usually calculate the derivatives numerically in neural networks. As a result, not being smooth is not a big issue usually in neural networks, okay? Huber and Kerr divergence. So Huber loss is a combination of mean squared error and mean absolute error loss function. So do you remember mean squared error L2 has issues with outliers? Mean absolute error has issues with being non-smooth. Huber says let's have the best of two worlds. Huber loss is this. So for smaller numbers, it uses a squared L2 norm. Why? Because at origin, for small numbers, it's a smooth. But for large numbers, L2 norm exaggerates outliers. It's not good. So for large numbers, I use L1 norm. So basically, if you illustrate it, it becomes something like this. At the small values, it's like L2 norm, but later it becomes like L1 norm. Okay, that's one thing. This is Huber loss. Scale divergence loss, as I said, this is this. So it is between two probabilities, right? And it's defined as this. Okay. Its form is very slightly similar to cross entropy. They are related a bit. Okay. Scale divergence. And as you see, obviously they are not, it's not symmetric. It's not symmetric. And by the way, we have a very symmetric version of scale divergence. That's Johnson something divergence. I don't remember, but you can Google it. Johnson divergence. I think it was the it says scale divergence of P and Q plus scale divergence of Q and P over 2, something like that. It becomes symmetric. Okay. And where were we? Okay. So now assume I have softmax. So at the end of the neural network, for example, it becomes 0.001, 0.09, 0.9, something like that. Okay, softmax. And also I have, so f of x is the probability of f of x is the output of the softmax of the neural network. Y, probability of y is the target, one hot encoded target label. So for example, it is 0.0001, right? So I have this probability distribution and this probability distribution. I want this to be very similar to the target. Minimize this difference between them, right? So I minimize the scale divergence. I can do that too. Hinge loss. If there are two classes, we can have true labels as -1 and 1. In this case, we can use this hinge loss. Hinge loss is this. What is this notation? I have defined it here. Maximum of something and 0. Okay. This is called a standard hinge loss. used a lot in deep learning. Also, it's used in triplet loss, which we'll see soon. Okay. We have seen it in another case too. Where have you seen that before? It's ReLU activation function, right? Similar to ReLU activation. Here also m is greater than 0 and it's a margin. What does it mean? Basically, it means that as long as this is greater than 0, minimize it. When it becomes less than 0 or less than 0, ignore it. Stop it. Don't need to train anymore, right? The loss becomes 0. And that's why it's margin. So by changing this margin, you can change when this becomes 0 or negative, right? So if the signs of the estimated and true labels are different, then the loss is positive, should be minimized. When the signs are the same and this happens, then it becomes 0, ignores it. If the signs are the same, but this happens, the loss is positive and should be minimized. Okay, these 3 cases might happen. Okay. By the way, let me think. Why does the third case is it important? Because the estimation is still correct, but not with enough margin from the incorrect estimation. You see that? So in case 1, the estimated and true labels are different in terms of sign, right? Because when does YIFO when is so YI is plus minus 1. FOXI is the output of neural network for XI is either it's some value, right? So it can be greater than 0 or less than 0, some float value, right? When they are, and we use, for example, threshold 0. As a result, when FOXI is greater than 0 and YI is plus 1, that's good. When FOXI is less than 0 and YI is less negative 1, that's good. But if they have different signs, then what happens? YIFOXI becomes negative. With this negative behind it becomes positive, plus margin becomes greater than 0. And that's problematic and it needs to be minimized, right? But when they are with similar signs, this becomes positive. With this minus behind it becomes negative, and assume that this float value, its absolute value, is greater than m. Then this becomes negative and done. It's good enough. However, the estimation might be correct, but its value might be less than m. It says continue training that, because we haven't reached that confidence yet. Confidence of margin m, right? We also have cross entropy loss function. So for cross entropy, we at the end we use C number of neurons rather than 1 neuron in the last layer. C is the number of classes, right? And then we use softmax or sigmoid. Let me tell you what. Assume I have 3 classes. I use 3 neurons at the end with the softmax activation function, right? And then I use cross entropy for classification. Now consider I have 2 classes. I have 2 options now. One option is that I use 2 neurons at the end, and again I use softmax activation function and I use cross entropy. But usually people do another thing when we have 2 classes. What do we do? Rather than 2 neurons, you can have only 1 neuron, because the probability that I am in class 1 is 1 minus probability that I'm in the other class, right? As a result, they usually use 1 neuron for binary classification, and they use sigmoid activation function, which outputs between 0 and 1, the probability, right? So far clear? Okay, then we use cross entropy. Cross entropy shows how different these are, so we need to minimize it. By the way, yi here is one hot encoding. What is one hot encoded label? For example, I have 3 classes. So class 1, class 2, class 3. For class 1, I use 001. For class 2, I use 010. For class 3, I use 100. This is one hot encoding. Why is it useful? Rather than using these labels, why is it useful to use one hot encoding? Because there is a flaw with the integer labels, 1, 2, 3. Because 3 has distance 2 from 1, but 2 has distance 1 from 1. So the distances of classes in terms of labels differ. But who says that class 3 should be farther from class 1 than class 2? Who says that? We use one hot encoded labels so their Hamming distance is the same. Right? So minimizing this loss separates classes for classification. This separation of classes also gives us discriminating embedding. You see that? Discriminating. Again, do you remember? 1 to the last layer can be used as the embedding layer, which separates the classes. Metric learning by Siamese networks. That's also important. One of the important deep metric learning methods is Siamese networks. What is it? It is used a lot for feature extraction. It's very useful. I have several papers on Siamese networks. Okay. Siamese network was originally proposed in 1993. It's a network consisting of several equivalent subnetworks sharing their weights. Siamese in English apparently means twins, something like that. So that's why it's called Siamese. So we have subnetworks sharing their weights. Okay. Usually we have either 2 subnetworks or 3 networks. 2 networks or 3 networks. Sharing their weights. So their weights are the same. Okay. When we have 2 networks, we usually use contrastive loss. I will tell you what it is. Contrastive loss. For this, we usually use triplet loss. Okay. And when we have 3 networks, it's also called triplet network. What is the goal? The goal is that the goal of these loss functions is the goal of Fisher discriminant analysis. Fisher discriminant analysis, which was proposed a century ago. For more information, see my statistical machine learning course. Okay. Fisher, Ronald A. Fisher, proposed an idea which dominated supervised dimensionality reduction or supervised manifold learning completely. All supervised manifold learning algorithms which proposed afterwards have this idea. Let's decrease the intra-class variances and increase the inter-class variances. This separates the classes. Again, let me repeat. Increase the inter-class variances and decrease the intra-class variances. Right? Triplet loss, contrastive loss, they are all doing this idea. Okay? But not using Fisher discriminant analysis, using another thing. But the idea is the same. Okay. So, by the way, I have a paper in my paper I have combined triplet loss, contrastive loss, and Fisher discriminant analysis. Okay. So, for training Siamese networks, we need to prepare its data. We can't use raw data. We need to prepare pairs or triplets of data. How do we do that? For pairs, we randomly get one each time. We get 1 point from one of the classes as anchor point. And also, we get either a random point from the same class, we call it positive point, or a random point from another class, we call it negative point. So anchor positive, negative. Then we will have pairs of anchor positive and pairs of anchor negative. For triplet, we'll have triplets of anchor positive negative, where in every triplet, anchor and positive are from the same class, maybe different classes, but from the same class, right? But negative is from another class. And we are sampling them randomly, right? So I think you understand what I mean. How can we find positive? Either we get positive from the same class, or we can augment or tweak that anchor a little bit. For example, we have it and we rotate it. We add some noise to it, right? So even if we don't have class labels, we can generate some triplets using this technique of augmentation, right? The positive point is also called neighbor point. Negative point is also called distant point. By the way, I said we generate them randomly, right? There are some techniques to generate them wisely. What do I mean? This is called triplet mining. Triplet mining. It says that rather than randomly selecting positives and anchors and negatives and anchors, consider maybe the hard case scenario or the easy case scenario. For example, what is the hard case scenario? The hardest case. So when anchor and positive are similar to each other, network gets happy. Let's make network angry, make it hard for network, but when we take hard on network, network learns better, right? What is the hard case scenario for network? When positive is very different from anchor, but negative is similar to the anchor. So in other words, hard case is farthest positive, nearest negative. The other way around, easiest is nearest positive, farthest negative. We can have several cases, right? So we can, for example, say let positive be random, but negative be hard. Or so we have triplet mining methods. I also have paper on that. You can see that. Okay. So yeah, consider these pairs. This is anchor positive pair. These are anchor negative pairs. Where NT, I think, is the number of triplets or number of pairs. So again, we can also have triplets, anchor positive negative, right? If we consider every point of data set as an anchor, then the number of triplets becomes the number of points in the data, right? Of course. We can have various loss functions for Siamese networks, which use pairs or triplets of data points. All of them try to push the positive point toward the anchor point and pull away the negative point from the anchor point. Do you remember I said they want to increase the interclass variance? How do they do that? By pulling away the negative point from the anchor point. They also want to decrease the intraclass variance. How do they do that? By pushing the positive point toward the anchor point, right? How can we implement Siamese network? How can we do that? We can either have several networks in the memory, but we use the same weights, but that's a dumb way to do that because it uses memory and etc. Because we need to copy the weights. Why do we store equal weights? We can have the same network, but feed it several times. Feed anchor to it, then feed positive to it, then feed negative to it. We'll have embedding of anchor, and embedding of positive, embedding of negative, right? Did you understand what I'm saying? By the way, in backbone, for the subnetworks, we can use any network. We can use fully connected network. We can use Siamese, we can with ResNet network, DenseNet network, convolutional neural network, right? We can use anything. LeNet as backbone. You already explained this. There are two ways to do that. We can use several subnetworks in memory, or we can use only one subnetwork in memory and feed it several times. Second approach is more recommended. and memory efficient. Okay, we are out of time. We'll continue this in the next session. So we'll talk about triplet loss, contrastive loss. Contrastive loss was proposed by, I guess, Google. No. Contrastive loss was proposed by Facebook, Likun etat. Triplet loss was proposed by Google, FaceNet. Okay, so big companies propose these loss functions. Okay, don't forget to do your assignment. It has great. Thank you.